We've been talking a lot about different kinds of chemical reactions, and now we're going to shift our focus a bit to focusing on how energy is involved in chemical reactions. So first, a quick review. When we talk about energy, energy tends to be classified into two main types of energy. And we have kinetic energy and we have potential energy. These names, kinetic, relates to movement. And this is what kinetic energy is about. Usually when we talk about kinetic energy, we're going to be using this idea of particles moving and that the kinetic energy of those particles is equal to 1/2 mv squared, where m is the mass of the particle and v is the velocity. And this is really a vector quantity, but we're not going to worry about that in this class. Vectors mean that they have size and they have direction. We're just going to go ahead and not worry about the direction. So all of our particles, regardless of type, are going to be moving. So we just recently talked about gas particles, and we know that gas particles, these are moving constantly in little paths, trajectories. And they can move a lot, right? Anytime they happen to be in a container, they can move anywhere in that container. If we think about liquid particles, we shouldn't be too surprised that liquid particles are moving around as well. And we can see that in the sloshing of a liquid inside the container, but of course, this is still a condensed phase. And so those particles, they can't go anywhere in the container because they stick to each other. And even though solids look like they aren't moving, solid particles are vibrating on the bond level. And we haven't talked very much about those bonds yet, but we'll get more into them in a little while. And so, although you don't need to really get into the details here very much, it's good to kind of keep this in mind. So one of the examples that I want you to take a look at for liquids moving around, I've actually posted a little video about the diffusion of these particles. And so in these experiments, what I did was I took some cold water and I took some hot water. And I took a sample of water that had just come to a boil and water that I had put some ice cubes in. And you can see how quickly those particles are moving around based on how quickly they diffuse a food coloring sample. So I put a drop of food coloring in each one and wait. So the natural movement of the liquid particles is going to give you an idea of how quickly those water molecules in the boiling water are moving compared to the water molecules in the ice water. So the speed of our movement of all particles depends on the temperature. We just talked about kinetic molecular theory and how speed depends on temperature, and the kinetic energy of those gas particles depends on temperature. And you can really see this demonstrated in that short video. So take a look at it a little later on. When we talk about potential energies, potential energy is sort of a weird name. I prefer to think of this as stored energy because potential energy sounds like it's not really energy. And it is energy, it just happens to be stored to be used for other things. So when we talk about chemicals, one of the big ways that we store energy is in electrostatic potential. This is a fancy word, but really all we're talking about here is charged particles. So the energy that's related with charged particles is governed by Coulomb's law, which says that if you have two charged particles separated by some distance d, the energy of their interaction here, how strongly they are attracted or repelled, depends on how far apart they are, how big these charges are, and then if they are oppositely charged, then this would be an attractive force. And if they are the same charge, then this would be a repulsive force. So when we look at potential energies and Coulomb's law here, better label it. What we're talking about are interactions between charged particles, which is atoms. All atoms are considered charged particles. So if we think about an atom, we model it as having a positively charged nucleus, and then we have negatively charged electrons outside it. And so these charges certainly are attracting each other. And this is true. And if I have another atom with another charged nucleus and some negative electrons, then this nucleus and these electrons are attracting each other, and this nucleus and these electrons are attracting each other. And you also have repulsions. Probably the nuclei are not getting close enough to feel very much repulsion, but you have both repulsion, I should have color-coded better. So these guys are attracting to each other, and attractions. And depending on the size of the nucleus and how many electrons you have and how far apart these atoms are, you're going to get different amounts of attractions and repulsions. We also get this when we have ions. Right? When we have something like sodium ion and chloride ion, the fact that these two have opposite charges from each other means that you are going to get attraction between those two ions. Now, of course, the nuclei would still repel each other, but the positive charge and the minus charge here in the outermost shell of those electrons is going to set up an attractive force. So imagine that you have now a calcium ion and some chloride ions. This also is going to have attraction. But notice that the charge on the calcium is a larger ion charge. And larger ion charges, if we look back up at Coulomb's law right here, right? If you have a larger charge, you're going to have a larger energy associated with that attraction. So that's something to be aware of. The larger your charge is and the smaller your distance, the more attractive energy you're going to have. So this counts as a potential energy, and when chemical reactions occur, we have some bonds broken, and some bonds are being formed. And this both absorbs energy and releases energy. So breaking bonds requires energy. And so depending on how we have are, how many bonds are broken and what kinds of bonds are broken and what kinds of bonds are formed, then sometimes there can be a net release of energy or a net absorbance of energy. So in order for us to talk about this release and absorbance of energy, we need to be able to talk about where the energy is starting and where it is ending. And so when we talk about this, we're going to talk about our system, and that's usually the chemical reaction, or where the reaction is taking place. And then we're going to talk about the surroundings, which is everything else. So if we have energy that is added to the system, we're going to give that a positive sign because it's being added to the system. So we would call this endothermic. And when we talk about that energy, we're going to usually use a Q, and we're going to say Q is greater than 0 because we've added it to the system. But we can also have energy released from the system. And so because it's coming out of the system, we give it a negative sign, and we call this exothermic. And we say Q is less than 0. So notice these names, therm here, this sounds a little bit like thermometer or thermostat, and this relates to the kind of energy that we are looking at. These energies are heat flow. They are a release of heat energy or an absorbance of heat energy. And that's what we use when we're talking about Q. Q is equal to heat flow. So when we are looking at these energies and we talk about this therm, that brings us to the overall name of this chapter, which we're talking about thermodynamics. And thermo means heat. And dynamic, usually we think about that as being something that's active. So we can think about movement. Movement of heat. Heat flow. That's our focus. Okay, so when we talk about heat flow, and when we talk about thermodynamics, we need to focus on that each system has a certain amount of internal energy. And depending on which book you use, our book uses an E, but sometimes I see books using a capital U as well to talk about internal energy. So just if you see either one of those mean internal energy. And each system has an internal energy, which is the sum of all the kinetic energy and the potential energy terms that are associated with it. So all the particles that are moving, everything that's happening, all the attractions, all the repulsions, everything, that all adds up to its internal energy. And the internal energy is not something that we can usually measure because there's so many complex interactions. So instead of measuring each of these individual ones, we focus on the change of internal energy. And we're going to use this delta sign, that's like a triangle, to focus on, to label this as change. So this would be the final amount of energy minus the initial amount of energy, specifically the internal energy here, but any kind of energy is going to have a change in initial. So when we focus on these changes, we have two main parts that we're going to look at. Specifically when we look at gases, but we can look at them with other parts too. We're going to have heat flow and we're going to have work. So heat flow we already talked about, that's Q. Work, we're going to use a lowercase w for this. And when work is done on a system, usually it's involved in compressing a system. This is figure 618 from our book, and this is showing us what is happening when we have work being done on a system and when we have work that the system is doing on its surroundings. So here was our little container. We've now squeezed our system. This is a gaseous system. So we're squeezing it down. We are compressing it and decreasing its volume. We are doing work on the system at the same time. This is the diagram of what's happening inside an internal combustion engine. And so if you squeeze it down enough, then you can ignite this. The fuel explodes and it expands. And that does work on the surroundings because we now have this system pushing all of the cylinder and making it expand. So this is work being done on the system. This is work being done on the surroundings by the system. All right, so even though we are introducing these terms, I'm probably not going to focus very much on work. I am mostly going to be focusing on heat flow and what this looks like for our systems. So when we talk about heat flow, we have two main units that we're going to use. Calorie, which you are familiar with from talking about food. And this calorie is defined as the amount of heat flow or heat energy needed to increase 1 gram of pure water by 1 degree Celsius. So 1 gram of water is about 1 milliliter. And when we are increasing it by 1 degree Celsius, it's actually a very specific degree. It's like from 14.5 to 15.5 degrees Celsius. But anyway, it gives you a general sense. This is not a huge amount of energy. And when we are looking at nutritional calories, so on a food label, these are really kilocalories. So we use a big C for the kilocalorie, is equal to 1,000 little c calories. More commonly, though, we're going to use the unit of joule. Joules, and this has an abbreviation CAL, this has an abbreviation capital J. Joules are related to calories in that 1 calorie is equal to 4.184 joules. So joule is not a very big unit either, and so often we will instead use kilojoules, 1,000 joules. So when we are looking at energy, we're going to describe the amount of energy flowing into or out of a system mainly by looking at joules, but occasionally by looking at calories as well. Now, even though I just talked about heat flow, more common even than talking about heat flow is that we use a specific term for heat flow. It has another name. It's called enthalpy. And if you studied chemistry before, you may have heard this term before. We use a capital H for enthalpy, and just like internal energy change, we use delta H to talk about changes of enthalpy rather than just abstract how much enthalpy does something have. Enthalpy is not an absolute value. It is always a relative. So we always are talking about changes in enthalpy, not about absolute enthalpy. There is no absolute zero for enthalpy, even though there is an absolute zero for temperature. So all kinds of things involve a heat flow. All kinds of things involve enthalpy. If you have an ice cube and you leave it out on the table, you know that after a while it's going to melt. And what's happening to that ice cube is that you have some enthalpy flowing in. So let's see, what would be that sign? It's going to be positive because it's flowing into the ice cube. The ice cube is our system. So we have enthalpy flowing in, energy, heat flow is flowing into that ice cube from the surroundings, from the warm air of your room, and it transfers it into the ice cube to break up those bonds that are holding this as a solid. And so we would have solid liquid or solid water that turns into liquid water because energy is added for this reaction from the surroundings. So this is just one example of energy. Here's a fun activity that you can try at home. If you have some hydrogen peroxide, and if you have some dry yeast, so not nutritional yeast, but for cooking, and it's even more fun if you have some dish soap and food coloring. So if you have these things, give this a try. Take a tall glass or a tall vase or a water bottle, any kind of a bottle will work, maybe about 16 ounces, and add about 1/2 cup of hydrogen peroxide. The 3% stuff from the store is perfectly fine. About a tablespoon of dish soap, food coloring if you want, and then stir in about a teaspoon of active dry yeast. And so, make some observations. You might think about what your balanced equation is, and make sure as part of your observations that you feel the sides of the container. Think about if you can describe what you think might be happening in terms of energy flow. Okay, I'd love to hear if you decide to do this reaction and make some observations here, and then let me know what you think.